We're at a funny time in history where the most powerful space telescope ever launched, James Webb, is capable of observing the atmospheres of exoplanets. And of course, one of the top priorities is to look at the atmospheres of the TRAPPIST-1 planets and other Earth-sized worlds orbiting around red dwarf stars. These are the ones that can be observed. And then the question is, if we do make those observations and we do detect an atmosphere, will we detect water vapor in the atmosphere? Does that mean there's an ocean? Is this planet more Earth-like and more habitable than we had thought, especially because red dwarf stars are terrible. And in their early lives, they send out these mega flares that it's thought will scorch these planets. And so right now, we don't know whether these planets have atmospheres. But if they do, what can we learn from them? So my guest today is Evelyn Macdonald. She is a PhD candidate at the University of Toronto, and she worked with her collaborators on a new paper where they simulated a bunch of these planets, these Earth-sized worlds orbiting around red dwarf stars, and to try and figure out what kinds of climates you would expect to see, where if you put land masses. And then they're looking for, would you get enough clouds forming at the place on the planet that Webb can actually detect the presence, and how much data is it going to require, and what could that tell you about these worlds? So it's a very interesting conversation about finding oceans and atmospheres on red dwarf planets. All right, enjoy the interview with Evelyn Macdonald. Evelyn, we're at this point now where powerful telescopes like JWST, like some of the ground-based observatories, are taking us farther and farther, letting us be able to get a much better sense of what the planets are like around these M dwarfs. Where do you sort of see the state of the art right now of what we can learn about these planets going around M dwarf stars?
Well, there's lots that we're learning about larger, hotter planets like hot Jupiters. But for smaller habitable zone planets that are Earth-like in composition and size, we're really still looking for an atmosphere. That would be the first step, is finding out whether these planets actually can have atmospheres, because they're so close to their stars, and their stars emit so much radiation that it's not clear whether or not the planets are able to have atmosphere. So that would be the first step. But in terms of like actual habitability, it would be really great to tell if they have water vapor. And it would be even better to tell how much. But we're not sure how well we can do that.
I mean, I know that like right now the observations are in from Webb for, say, the TRAPPIST-1b and TRAPPIST-1c, and both of those are found to be airless. We've been reporting on some amazing atmospheric analysis, but these are larger planets around other kinds of stars. So, I mean, has anybody detected an atmosphere around any planet at a red dwarf yet that we know of?
Planet, yes. Earth-like planet, not so much.
Right. Okay. So like a sub-Neptune or something. Sure. Fine. Yeah. Okay. So a planet in,
like not even this. Planet.
A rocky planet with an atmosphere.
Yeah, I don't think so.
Yeah.
We're trying. The thing is, planets like TRAPPIST-1b and c are easier to observe because they are closer to the star. They're hotter. And that makes observations easier. That also makes them less likely to have atmospheres. So it makes sense that these are the ones that we're observing first, and it also makes sense that we haven't detected atmospheres on them. That doesn't mean that we won't detect atmospheres on ones that are in the habitable zone. I think it would be really great if we could, but we'll see what happens in the next few years.
But I mean, we got those observations, or the announcement of the observations from TRAPPIST-B and C pretty quickly into Webb's operations. And I know that the measurements have taken for some of the other exoplanets. Is it an issue that the data are difficult to crunch down, or is it sort of a fainter observation? Not enough time on the telescope yet?
Yeah, it's also a different type of observation. So those first ones were emission spectra using eclipses, I believe. So, like actually looking at the thermal radiation from the planet, whereas for cooler planets, they'll be looking at transit observations instead. So looking at the light passing from the star through the planet's atmosphere, if there is one. And those take longer. And it's also just harder to make the observations when the planets are cooler because they're fainter, they transit less often. So we're getting there. I say we. I'm not directly involved in any of these observations.
No,
so
I understand,
don't have any
but just
insider information.
Yeah, no, well, yeah, that would have been great if you did. No, there was a paper that came out, like I think I read it just yesterday, where someone was saying, like, if we want to do a proper atmospheric evaluation of terrestrial exoplanets in the habitable zone around red dwarfs, we're going to need on the order of hundreds, if not thousands, of hours of JWST time, and I'm certain that amount of time has not been handed out yet. And so I guess we were hoping for a slam dunk, like something really obvious, but nope. Turns out it's going to be more difficult than we expected. So I guess let's imagine that you do get observations of these exoplanets and you're trying to sort of make sense of what you're looking at. What this is more where your work is, to think about, I guess, what could we see in those exoplanet atmospheres?
Yeah. So the easiest thing to detect, if it was there, would be carbon dioxide, because it has a very large peak that goes high up in the atmosphere. But so that would be like the sign that this planet has an atmosphere and we should keep looking at it. But in my recent work, I was looking specifically at trying to connect things we can't observe directly to what differences they might make in observations, and specifically observations of water vapor. So we assume that these planets are tidally locked with the same side always facing the star. So they have a hot day side and a cold night side that we assume is frozen. And somewhere on the day side, there is this ice-free region in the middle, because that's where most of the sunlight is hitting the planet, so it's warmest. And so the idea was to put land in that ice-free region and see whether that makes a difference in the climate, because in that warm part of the planet, whether or not there's liquid water will affect how much water makes it into the atmosphere. Because if all of the water's on the night side, then it's covered in sea ice. And so the planet has water, but it's trapped. And it can't enter the atmosphere as well. So the planet will be much drier. And so I was looking at whether where we put land and how much land there is can affect how much water vapor shows up in the transit spectrum. And we found that the answer is like, yes, but the signal is really small and it's kind of complicated to disentangle what's causing these differences. But I think finding water vapor in the first place would be a good thing.
Yeah, of course. I remember last time we talked, I interviewed you a couple of years ago with your advisor, I think, and you guys surprised me, because the traditional idea of these tidally locked planets is that one side is baked bone dry, and then the near side is tidally locked and is like a desert that never ends, and then the far side is in eternal darkness, and so is completely frozen over, and then you may get this terminator around the edges. But sort of your understanding is no, in fact, it's more like a jungle on the near side than just a straight up desert. And so you would get water if there was an ocean on that side, or a significant amount of water. And so that's what you're sort of expecting, is that you would get this, that the near side is going to be having a more jungle-like release of water into the atmosphere.
Yeah, so the caveat is it depends how much water the planet actually has. And there are a few different regimes that it can end up in, depending how much water it has, depending how fast it's spinning. Like it's not rotating with respect to its star, but it's still orbiting the star. So that rotation does still play an effect in climate. But in our simulations, we've kind of assumed an infinite water inventory from the ocean. and then that water enters the atmosphere and moves around and can end up on the night side. But if we put ocean on the day side in these models, we assume it doesn't dry up. So yeah, we find that in pretty much every case, no matter where we put the land, if there's some water, it ends up at the substellar point. So in the middle of the day side, even if there's land there, the atmospheric circulation brings the water there. And so this is kind of similar to the Hadley circulation on Earth, where on Earth the sun shines down at the equator, and so the air, the surface is heated, and then that makes the air rise. And as it rises, it cools, and then the water precipitates out and you get rain. So on Earth, that's around the equator. On these planets, that's at the substellar point in the middle of the day side. And then the air circulates upward, like it goes up and then moves out toward the night side and then comes back along the surface. So if there's ocean on the surface of the day side elsewhere than the substellar point, the air coming back toward the substellar point will accumulate water evaporating from the ocean. And so then, regardless of whether there's land or ocean at the substellar point, we still get rain there. So you can kind of get this hydrological cycle that's trapped in the middle of the day side. But then, so that's where most of the water in the atmosphere is. That's where it's raining. But then the next question with that is, can we actually see this water in transit? Because transit spectroscopy doesn't look at that part of the planet. It looks at the terminator, which is the line dividing the day side and the night side. So we need to know if there's a connection between how much liquid ocean is on the surface, how much water is at the substellar point, and how much water is actually making it to the terminator in a way that we can detect. And the answer is that we find some connection, but it's just hard to tell the difference because of how small the signal is.
So, like, imagine I'm flying in space and I'm at the star planet L1 Lagrange point. And so I'm looking down at the planet from however many hundreds of thousands of kilometers away. What am I seeing? Like, assuming it does have an atmosphere and it has oceans and it has land masses on the side that's facing the star. I mean, is it one big swirling storm system, or like, what do you sort of anticipate it's going to look like?
And depending on how much land there is, you're probably seeing clouds and some ice, maybe some land. But yeah, we find a lot of cloud in the middle of the day side and also over ocean. But clouds are one of the hardest things to model in these 3D circulation models because they just matter on so many different length scales that it's hard to model them effectively. But you're probably seeing clouds, much to the frustration of all modelers ever.
Like only cloud? You're mostly seeing clouds?
I'm not sure.
Yeah.
It'll depend on what the surface is like, how much land there is.
Right. But then I guess what you're asking is, will those clouds extend all the way out to the terminator, or are you going to get this kind of bullseye?
Yeah. So we get some night side cloud as well. It's colder there, but actually one interesting thing we found was that at the terminator, so looking in transit spectroscopy, if you have a thick cloud deck, that kind of ends up like truncating your signal. So it looks like the solid surface of the planet is higher up than it is because the clouds are just blocking all of the light from making it through the atmosphere. And we're finding that in planets with more water vapor, there's more clouds at the terminator, with the result that the water vapor signal looks smaller than it does on drier planets, which have less cloudy terminators. So this is very dependent on the cloud model used. Like there's a huge uncertainty between models in how much clouds are going to matter and where they're going to be, how much of the night side is cloudy. We just know that clouds will be there and will probably affect things.
Right. And so I guess the question then is, if you do detect that water vapor in your observation. So if there is enough of that water vapor that makes it out to the terminator that is then visible when you get those transits, how much can you then apply that to how much water you think there is on the planet?
I think you should just be very excited that you found water.
That's it. Right. Right. Because
So,
that means liquid water on the surface.
possibly. Or I can't say for sure, but
right.
Certainly it would be a big deal to find water. That is a very good sign. But yeah, the other thing that I didn't mention that I also varied in the study was the amount of nitrogen in the atmosphere, so the actual surface pressure, the mass of the atmosphere, and that affects the circulation as well. And there's kind of some overlap between the effects of how much land there is, where the land is, and how thick the atmosphere is, and how much water ends up in this transit signal. So for a given amount of, or a given amplitude of signal, there are a few different climates that could be causing that, and a few different amounts of water, a few different placements of the land. So we might not know the details of the surface condition, but a lot of these climates could be habitable, just in different parts of the planet or under different configurations. So finding water doesn't mean it is habitable, but it would certainly be a very exciting finding.
Yeah. So I guess what else would you potentially like to look for? You mentioned looking for nitrogen in the atmosphere, obviously carbon dioxide, water vapor. Are there any other things that you might be looking for in the atmosphere of one of these exoplanets?
Yeah, so the thing about nitrogen is we can't actually really look for it directly. It doesn't really have much of a transit signal, but it does affect the climate. So that's why we varied it. But in terms of observations, lots of people have studied different biosignatures, so molecules that could be indicative of life under different conditions. So oxygen or ozone and methane together on Earth are a sign of life because they are not in chemical equilibrium. But a different planet with different chemistry could have different biosignatures or different explanations of why those things are there. But again, finding them at all would be a huge step. And then people can think in more detail about that planet and what might be going on.
Right. Now this, your research so far is based on what's been done, what can be done using observations during a transit of an exoplanet, of a one of these terrestrial planets going around a red dwarf star. But there is sort of future telescopes in the works. There is, Nancy Grace Roman is going to have a very powerful coronagraph on board. The Extremely Large Telescope is going to have a pretty powerful one. And of course, the Habitable Worlds Observatory. And so we're going to move into this era, hopefully, of direct imaging exoplanets. And I know we're now into speculation zone, so just, it's okay. But how would, if you had access to spectroscopy from something that was doing direct imaging of these exoplanets, how would you think that change what you would be looking for?
Yeah, so that would change, first of all, the types of planets we were looking at. With Habitable Worlds Observatory, they'll be able to observe Earth-Sun-like systems. So instead of M-dwarf stars, a Sun-like star, which is much hotter and bigger, and the planet is farther away. So they'll be able to directly image it. And that means that the planet's more likely to have an atmosphere in the first place because it's not so close to its star. And it also means that it's not tidally locked and more like the one example we know of a habitable planet, Earth. But yeah, again, they'll be wanting to look for similar things like water vapor, just the different type of measurements.
But I guess with those, you're seeing the planet from all angles throughout its orbit. And so you're not really dependent on waiting. You're not just getting that glimpse of the Terminator. You're seeing the entire world and being able to take a signal from that.
Yeah.
Red dwarfs are pretty terrible. They put out these pretty catastrophic flares, and I think right now, as where we are right now in 2024, there is hope that there are going to be planets with atmospheres. Do you have a sort of suspicion either way? Do you think it's going to turn out that these planets do have atmospheres, or do you think they're just too difficult an environment to be near a star with those kinds of mega flares?
I think the jury's still out. I'd like them to have atmospheres. I think it'll be hard to observe enough of them to know for sure. And the thing is, it's hard to conclusively have a non-detection. It's hard to say this planet definitely does not have an atmosphere. It's easier to rule out like thick atmospheres or certain types of atmospheres for a given planet. So yeah, it's possible that they could have atmospheres. Whether those atmospheres are capable of supporting life is an entirely different question. But I do think it's possible that some of them could, if they're able to hold enough relevant elements in their mantles for a long enough time scale, and then have a secondary atmosphere. So planets can, when planets form, they have a primary atmosphere, like mostly hydrogen and helium, and that doesn't survive on these smaller planets. All the flares from the star. But then through outgassing, so through like volcanism, for example, they can have a secondary atmosphere of more heavier molecules like nitrogen, CO2, stuff like that. So it's possible that some of these planets could have some kind of an atmosphere.
And I guess it's a timing thing, like how long it takes for that secondary atmosphere to show up. It might be that the star has gotten all of the tantrums out of its system, and now, and if the planet, I guess, maybe has a powerful enough magnetic field to help protect it from the particles coming from the star.
Yeah, at least the worst of the tantrums.
Yeah, yeah. And so, I mean, I think what you're saying is that we're not going to find a conclusive answer to this question probably for a very long time. We may continue to not find atmospheres, but that doesn't mean that there aren't any out there. It's just the search goes on.
Yeah, or we might find one. We'll see.
So where does your work go next?
Well, so I'm looking at trying to understand some of these climates in more detail. In particular, trying to understand what's happening on the night side of these planets with heavier atmospheres, with more N2 in their atmospheres, because we're finding that can change the circulation. So if you have a thicker atmosphere, you get more heat circulation away from the warm part toward the cold night side. So trying to understand what's going on there. And then beyond that, I'd like to start modeling some more sun-like host stars, or planets with more sun-like host stars, thinking about these upcoming missions, trying to understand what climates could be like for these different planets. But I do really enjoy working between theory and observation. So using these climate models to really understand the details of the climate and what might be possible, and then connecting these things we can't observe directly to what their observational signatures might be, to try to make the most of these really difficult and expensive observations once we get them.
I mean, I think about like making a video game, or like writing some science fiction novel where you're trying to imagine the climate on some world that is not Earth, and you think about different inputs and different, maybe a different history of the planet, and you do that as scientifically accurate as you can with very powerful computers to try and piece together all the dots. Do you run across a world and think, oh, I wonder what it would be like to live there? What would life be like on a world like that?
Oh yeah, all the time. I also like thinking about worlds in sci-fi and wondering how scientifically accurate they are.
Yeah. Have you got an explanation for like Game of Thrones?
I honestly I've not seen Game of Thrones. I'm sorry.
Okay, all right. Well, they've got this sort of weird long orbit where winters and summers are extended over long periods of time and appear randomly. But well, Evelyn, what are you obsessed with?
Oh, I'm obsessed with simulating these fake planets, I guess.
Yeah.
Getting to play with stuff in a way that doesn't necessarily make physical sense in order to isolate effects, and then trying to put it back into something reasonable. I like to think about the possibilities.
Yeah, I wonder about. Yeah, like I wonder about planets around the pulsar planets, or planets around white dwarfs, or planets in like double planets, like having a binary planet, or exomoons that are habitable, like, I don't know, indoor. I mean, I always think like the universe has probably come up with things that our imagination haven't even considered, and it's just a matter of time before we find them out there.
Yeah, absolutely. I think white dwarf planets would be an interesting opportunity, because the signal from the star is so much smaller that we can actually see the planet better. Exomoons are interesting because they wouldn't be tidally locked to the star. Like, their planet might be tidally locked to the star, but the moon wouldn't be because it's orbiting the planet. And the difficulty with both of those things is observations, but that does not stop anyone from writing some cool sci-fi about it. So someone please do that and let me know.
Yeah, that sounds great. Well, Evelyn, thank you so much for your time, and good luck with your research and getting your PhD.
Thank you.
I hope you enjoyed that interview with Evelyn Macdonald. Now, I'm going to share some more thoughts shortly, but first, I'd like to thank our patrons. Thanks to Abe Kingston, Andrew M. Gross, Antonio Lofilar, David Giltonen, Dougie Stewart, Dustin Cable, Jeremy Mattern, Jordan Young, Josh Schultz, Mark Anstis, Paul Rohrbach, Stephen Krasaki, Stephen Filer Munley, and Vlad Shiplin, who support us at the Master of the Universe level, and all of our other supporters on Patreon. It's so strange to be at this time where we are in between this knowledge that we now have the tools to potentially detect the atmospheres on Earth-sized worlds orbiting around at least red dwarf stars. I mean, later on, we'll get to the point where we can detect them around sun-like stars, but we're going to need to wait for a few more telescopes to come along. And we don't know the answer to this question. And then future us, like I know 10 years from now, future Fraser is going to look back and say, here's how we know how it turned out. We know that exoplanets with atmospheres around red dwarf stars are everywhere. And it's a bold new era of realizing just how much the life can be around almost any star out there in the universe. Or it's been 10 years, astronomers have looked and they've looked and they've looked, and so far, no red dwarfs have terrestrial planets with atmospheres. Like, clearly they are ruining the chances of life. And red dwarfs are the most common stars in the universe. And so, it makes a big difference on whether or not these stars. And this is the question that can be answered and will be answered very soon. And yet we don't know the answer today. And we're going to watch this unfold in the months and years to come. All right, I've done plenty of interviews about red dwarf stars and habitability and exoplanets, so I'll link a couple here. Thanks, everyone, and we'll see you next time.